So we have been talking about rotational mechanical systems on the last turn. So the treatment is very similar to translational mechanical systems. However, there is one important difference, and that is because of the presence of gears in rotational mechanical systems, which are very common devices which are used to change the angular velocity torque relationship from one side to the other. So this is the slide from your book. So you have two gears here, two different dias, R1 and R2, and consequently you have two different set of teeth, number of teeth, N1 and N2. The teeth are similar in size and dimension on both the gears. That is why there will be more teeth on the bigger gear, the gear with the bigger radius, and less number of teeth on the smaller gear, right? And if there is a torque angular displacement relationship which is given by T1T and theta 1T on this gear, it is going to be different on this gear. So T2T, theta 2T on the two side on the other gear. And the other important thing is that the direction of motion is going to change. So if you're rotating this like this in the clockwise direction, then it is going to rotate this gear in the counterclockwise direction. What is the relationship between the torques, right? So suppose you're exerting a torque T1 here. So what is the relationship between the torque T1 that you're exerting here on this shaft to the torque T2 that you're getting on this shaft? Similarly, what is the relationship between the angular displacement theta 1 that you're getting on this shaft to the angular displacement theta 2 that you're getting on the other shaft? So this is what we're going to see today, and then we're going to incorporate this in our study. So what is very obvious is that the displacement at the point of contact, the linear displacement at the point of contact here, this is the point of contact, is going to be the same, the displacement along the arc. So what we can do is very safely, we can say that R1 theta 1, that is the linear displacement at the point of contact for gear 1 should be equal to R2 theta 2, right? That means theta 1, and since theta 1 and theta 2 are functions of time, so that means theta 1t divided by theta 2t is going to be R2 by R1, right? And since the teeth are proportional to the radius, we already know that R1 is proportion, N1 is proportional to R1, and we already know that N2 is proportional to R2. So we get theta 1t by theta 2t. We can write down because of this proportionality relationship. This means that N1 by N2 is equal to R1 by R2 and vice versa. So this means that we can write down theta 1t by theta 2t by is given by N2 by N1, right? So which means that theta 2t is going to be N1 by N2 theta 1t. So 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 this is your theta 2t, this is your theta 1t, and this theta 1t would be multiplied by N1 by N2, which essentially means that if you have a smaller gear here and a larger gear on the right hand side, then the angular displacement for the gear on the right hand side, the bigger gear, the angular displacement is going to be less. So that's obvious because many rotations of the smaller gear will correspond to one rotation for the larger gear, right? When you have this relationship for theta 1 and theta 2, you can also have a similar relationship for omega 1 and omega 2. So for omega 1 and omega 2, because this theta 1 displacement and theta 2 displacement, we are assuming that these two displacements are taking place in the same time. So what you're basically saying in this is that you're moving the smaller gear by you're moving the smaller gear. You're moving the just a second. You're moving the smaller gear by a distance of theta 1t in time t. So the larger gear moves by a distance of theta 2t in the same time t, which actually means that the relationship between theta 2 and theta 1 is also the relationship between omega 2t and theta 2t. So if you theta 1t. So if you differentiate this equation with respect to time, you get d theta 2 by dt, which is omega 2t, is equal to n1 by n2 uh, omega 1t, right? So the angular velocity of the larger gear is going to be smaller. And assuming that these are lossless gears, so the power that is transmitted from the smaller gear to the larger, or from one gear to the other, would not change. So which means essentially that T1T, the torque multiplied by the angular velocity on one side, should be equal to the torque multiplied by the angular velocity on the other side, which means that you can write down T1 T1T by T2T. You can write down this as uh, omega 2T by omega 1T, right? Which is going to be, since the relationship between omega 2 and omega 1 is equal to n1 by n2, so it is going to be n1 by n2, which means that T2T, which means that T2T is going to be n2 by n1 T1T. And if you want to draw this using the block representation, so this is your T2T, this is your T1T, and you have in between N2 by N1. That means since N2 is larger as compared to N1 in this example, so you are getting increased torque on the right hand side. So you're getting increased torque T2. So you're compensating for linear displacement, for angular displacement and angular velocity, by getting an increased torque on the other shaft, right? So these two relationships we have to remember, right, for torque and for angular displacement and angular velocity, right? So now coming to an example which has in which you actually have a gear, right? So you have a system like this, again, a mass spring damper system, inertia spring damper system, in which you have you're applying the torque, through a gear with ratio n1 by n2, right here. So you're applying a torque, let us see. You're applying a torque in the clockwise direction, and you're getting an angular displacement in the clockwise direction, and the number of teeth are n1 here. But because it's a gear system, so the displacement that you get here is actually in the counterclockwise direction. So theta 2 is going to be in the counterclockwise direction. Now, how are we going to solve this? Okay, so let us first examine the number of degrees of freedom. Does this attachment of this gear here change the number of degrees of freedom? Actually, this is a 1 degree of freedom system, which we have already seen. But if we have this, if we put this gear, does it change the number of degrees of freedom? It does not, because if you fix this displacement, for example, the displacement of the inertia J, if you fix this, if you say that this J is not moving, then you can very easily see that you will not be able to rotate n1 also. You'll not be able to rotate, because when you fix J, you're fixing n2, and when you're fixing n2, you're fixing n1. So this is a single degree of freedom system. Okay. Now let us see whether how to solve this, right? So suppose uh, you want the transfer function of this system, right? So you want theta 1s by t1s, right? So what we have done in this case is try to see what is the torque that finally gets applied to the shaft. So the torque gets multiplied by this T2 torque, and the torque T2 on this shaft would be obtained by multiplying it with N2 by N1, right? So that's what we have done. T2 is equal to N2 by N1 into T1. So the torque on the gear with N2 teeth is going to be N2 times N1. The torque on the gear on with teeth N1. So you have the torque on this shaft is going to be counterclockwise like this. It's going to be T1T N2 by N1, and theta 2T is the displacement here. So we can write down from this, we can write down the governing equation for this. So if you write down the governing equation, the so let us look at this diagram. So so what is the torque? The torque is T1T N2 by N1, and what is the displacement? The displacement is theta 2T. So let us write this down. So in the S domain, T1S N2 by N1, this is the torque, is going to be equal to, and what are the elements that you have here? The elements that you have are the inertia, the damper, and the spring. So let us write down, this is going to be Js square plus ds plus k into theta 2s, right? We can write down theta 2s in terms of theta 1s. We already know that theta 2s is going to be, uh, see, we have written theta 2 is going to be n1 by n2 into theta 1. So we can write this down. Theta 2s is equal to n1 by n2 theta 1s. So we can substitute this equation in this. And what do we get? We get theta 1s n2 by n1 is equal to js square plus ds plus k n1 by n2 theta 1s, right? So we can write down T1s by theta 1s is equal to n1 by n2 whole square, right, into j square plus ds plus k. So if you assume this to be, if you call this to be a constant, say alpha, right? Give it a name. Say this is alpha is equal to n1 by n2 whole square. Then this is T1s by theta 1s is equal to alpha j s square plus alpha, so there is a theta 1 here also, alpha ds plus alpha k theta 1s. So what does this look like? This looks like a uh, like a, a like a system in which you have uh, an inertia which is given by alpha j, right? A spring which is given by alpha k, and a damper which is given by alpha d, where alpha is equal to n1 by n2 whole square. And here you're having a torque in the counterclockwise direction and a displacement in the counterclockwise direction. So it seems that the effect of the gear is to convert. So this is what you have drawn. This is now the equivalent. This is now the equivalent diagram for the mass spring damper system that you have already drawn here, right? So this is the equivalent. And what does it show? It shows as if the as if you have moved the impedances from the uh, shaft on which they were to the shaft on which uh, the torque is actually applied, right? So, and what happened to the impedances? They actually got multiplied with, this is the example here. They actually got multiplied with n1 by n2 whole square, right? So this is what we got in return. So the actual system was this, and then when you shifted, when you wrote down the equations for this, you got an equation which gave you a system which is equivalently this. So what you can say is, what you have done in this is that you have moved the impedances from this shaft to the shaft on which the torque is actually applied. And when you did this, You multiplied all the impedances by a ratio which is given by n2 by n1 by n2 whole square, which is the number of teeth on the destination shaft divided by number of teeth on the source shaft. So what whole square. So what does the gear do? The gear actually equivalently changes the impedances that the torque is actually facing. And if you want to remove the gear and draw the equivalent diagram, right, what you can do is you can shift to any shaft, but the impedance that you shift to the shaft will be a reflected impedance, and it's it would be equal to number of teeth on the destination shaft divided by number of teeth on the source shaft, right? So this is what you get at the end. And to solve similar problems which have gears, this can be done very easily. So see, for example, in the second example, you have a gear system here, right? In this you have gears here. So the first thing is to see how many degrees of freedom does it have, right? So it will have 2 degrees of freedom, one degree of freedom. Uh, uh, See, these two inertia are coupled together. So this is 1 degree of freedom, but this damper is separate, and this can be moved despite this inertia being fixed, right? So this is a 2 degree of freedom system. So now, if you want to move everything to the shaft on which the torque is applied, right? How would you do that? What you would do is you would sorry. So this is not a 2 degree of freedom system. This is a 1 degree of freedom system. If you fix this inertia, you're fixing this inertia, and consequently, when you're fixing this shaft, you're also fixing this shaft. So this is a 1 degree of freedom system. Now, how do we move everything to the source shaft? So everything this if you want to move everything to the source shaft and draw the equivalent, so we'll take this inertia, we'll take this friction, we'll take this spring and multiply it with a ratio n1 by n2 whole square, right? uh, we'll move it from this shaft to this shaft, or if you want to move it from this shaft, if you want to move it from the other way around, like in this book, if you want to move everything from this shaft on which the torque is applied to this shaft, right, then you have to multiply with again n2 by n1 whole square. So if you multiply this j1 by n2 by n1 whole square, you get j1 n2 by n1 whole square plus j2. J2 is the inertia here. It is getting added up with j1. And similarly, this t1 is the inertia here. It gets added up by multiplying it with n2 by n1 whole square. It gets added up to the coefficient to the viscous friction here, d2. So this is the equivalent of fixed friction on this shaft. K2 remains the same. K2 remains the same. And what happens to T1T? T1T gets multiplied by N2 by N1. So it's T1T into N2 by N1. And this is theta 2T. Theta 2T is the displacement. So you can write down the equivalent rotational mechanical system by removing the gears. And once you have something like this, once you have something like this, you can easily write down the equations and find out uh, the transfer function, whichever transfer function you want to find out. I hope it is clear. So in this case, what we have done is that we have moved all these impedances that are on this shaft to this shaft, and to do that, what we do is we multiply them with the ratio destination number of teeth on the destination shaft divided by number of teeth on the source shaft whole square. So the number of teeth on the destination shaft is N2 and the number of teeth on the source shaft is N1. So J1 gets multiplied with N2 by N1 whole square, and since J2 is here, so you have to add it to J2. So this is the equivalent moment of inertia. D1 gets multiplied by N2 by N1 whole square, and since D2 is here, it gets added to D2, and the other things remain the same. Similarly, you also have to shift the torque and the angular displacement and see what is the nature going to be. And once you have this diagram, it is very easily after this to write down the transfer function for a system like this. I hope from these two examples, it is clear what to do when you have a gear in the rotational mechanical system. Thank you very much for listening.